All right, welcome to the second day this week. We're going to talk about atomic numbers and their masses. So an atomic number is the number of protons in the nucleus of an atom of an element. The number of protons actually determines the identity of an element as well as many of its chemical and physical properties. There are as many electrons as there are protons in an atom. So the atomic number also tells the number of electrons in an atom. Remember, the atom is neutral. So a neutral atom has the same number of protons as it does electrons. The atomic number tells us the number of protons. If it's neutral, it tells us the number of electrons as well. So here you can see, whenever you look at the periodic table, you will see a square that looks like this. This number here at the top is the atomic number. You'll see the symbol. The first letter is always capitalized. The next letter is lowercase. And it's important for you to remember to draw them the same way. So if you had capital C, capital D, that would not be cadmium, for example. You'd have to have a capital C and a lowercase d for it to be cadmium. If there are two letters, the second letter is always lowercase. The name is underneath the element symbol, and the average atomic mass is the bottom number here. The mass number is the sum of the protons and the neutrons in the nucleus, because remember, the electron's mass is negligible. So mathematically, it's represented as mass number equal number of protons plus that should be the number of neutrons. That is incorrect. So let me fix that. That should be number of neutrons. I apologize. Mass number is the sum of the protons and neutrons in the nucleus. Now, isotopes, we mentioned isotopes before, they have different masses. So they're going to have different mass numbers. And that is because they have different numbers of neutrons. They have the same atomic number, so it's the same element, whether it has a mass, if we have carbon and it has a mass of 12 or a mass of 13, it's still carbon. It just is a different isotope. Still have the same properties, but one has more neutrons than the other. Isotopes are identified by writing the name or the symbol of the atom followed by its mass number. So here we have neon 20, neon 21, and neon 22 here. You don't have to write isotope, neon full name 20. You could just do the abbreviation with the hyphen. It makes it easier. Let's do some practice. Again, pause your screen. And then try to answer this and then come back and see if you have it right. So if we use the periodic table, how many protons does oxygen have? How many electrons does oxygen have? How many neutrons does oxygen have? So let's answer these questions first. I'm going to change so that we are looking at a periodic table so that you can see here. Now I've gone to oxygen. Oxygen has an atomic number of 8. So how many protons would that be if we're looking at oxygen? Right, we'd have 8 protons. So here we'd have 8 protons. Now, if it's neutral and it has 8 protons, how many electrons does oxygen have? It has 8 as well. So let's go look at the mass of oxygen here. Always round up to the, or round, I should say, always round to the nearest whole number, because you're not going to have part of a neutron. So you always round to the nearest whole number. In this case, it's 16, whenever you're trying to determine the number of neutrons. And we take 16 minus 8 to determine the number of neutrons. Because remember, the mass equals number of protons plus number of neutrons. So to solve for the number of neutrons, it's going to be the mass minus the number of protons, which is 16 minus 8, which equals 8. All right, let's look at number 4. Number 4 says isotopes of an element have the same number of protons but different masses. Why is this? What determines the extra mass? Is it the number of protons, the number of neutrons, or the number of electrons? It's the number of neutrons. So the number of neutrons is differ between them. For example, you have carbon 12, which has 6 neutrons, 6 protons, and 6 electrons. And you have carbon 13, which has 6 protons, 6 electrons, but 7 neutrons. So same element, but it's a different isotope because it has 1 extra neutrons. Let's come back to this. Now, here's a little joke for you. We have the periodic table, and he says, right there, do you see it? Oh my gosh, I can't believe it. It's the element of surprise. So the development of periodic table, I could hear your eyes roll. That's how my son's eyes would be right now. But you know, you thought it was funny. So 1860, you have several different elements that are already identified. Almost half of what we have now, there were 60. And they noticed that there are similar properties. There is no periodic table at this point. People are just trying to organize them however they see fit. There's not one that is universally accepted. Differences were noticed among groups of elements as well as individual elements. So here you have one periodic table that someone in 1898 designed. To me, this looks pretty confusing. Here's another periodic table that someone designed. And it might, of course, make sense to the person who designed it, but it's not intuitive to me looking at it. So J.W. Dobereiner classified elements into groups of 3, which he called triads, according to their properties. The atomic mass of the middle element lies about halfway between the other 2 members of the triad. So density, melting point, and boiling point all increased as atomic mass increased. And that was a trend he noticed, and that's why he put them into those triads. You can see the halide triad right here, that the atomic mass increased, the density increased, melting points increased, and the boiling points increased. And he got excited by breaking them down this way, and he's introducing it to his fellow scientific friends. Because this suggested that the properties of an element are actually related to its atomic masses. And Dmitry Mendeleev, who was a Russian scientist, developed a periodic table, and then he realized that the chemical and physical properties of the elements repeated in an orderly way when organized according to increasing mass. And he organized it so that elements with similar properties were placed in horizontal rows. Let me bring your attention to this. Repeating properties is periodicity. So that's why it's called periodic table, because periodically the properties repeat itself. So if you ever wanted to know why it was called the periodic table, that's why. Periodicity is the tendency to recur at regular intervals, hence periodic table. Mendeleev correctly was able to predict the properties of several undiscovered elements using his periodic table, which is why his theory of periodicity was accepted universally by others, because he was able to correctly predict the presence of selenium and germanium. He left gaps in his periodic table and said, we haven't found these elements yet, but when we do, they're going to have densities like this, boiling points like this, melting points like this, and masses approximately like this. And people thought he was a little crazy, but whenever they discovered those elements, they realized that he was actually correct. Now, with our modern periodic table, we have 118 elements that are arranged not according to atomic mass, but atomic number. There's actually 2 elements on the periodic table. If you look at masses, they're switched, but their atomic numbers are arranged correctly. Periodic law is just the physical and chemical properties of the elements repeat in a regular pattern when they're arranged in order of increasing atomic number. So here's our modern periodic table. And I believe it's iodine and tellurium, but this is, yes, it's iodine and tellurium that are switched, if you can see here. In this periodic table, we have the mass and atomic number close to each other. It's set up a little bit different than the one I showed you, but you can see it's arranged according to atomic number. Originally, if they followed Mendeleev's pattern, they saw that tellurium was here where iodine was, and iodine was where tellurium was. But they realized that the properties didn't fit like they did everything else. And that was an anomaly they couldn't explain until they arranged it by increasing atomic number. And then they realized it's the number of protons that give the properties to the elements, not the mass. Now, the relationship of the periodic table to the atomic structure, I already mentioned that a period is a horizontal row in the periodic table. The first period has only 2 elements because there can only be 2 electrons in that first energy level. A group is a vertical column. Sometimes it's called a family because they have similar characteristics, just like genetically, your family has similar characteristics. My mom used to joke with our family that she just stamped us out. We could be out in public in our small town and people would know exactly who we were just because of how we looked. My boys insist that I have a twin sister who is 5 years older because they say we look exactly alike. So families tend to have similar properties. That's why groups, which are vertical columns, go up and down, and are called families. And then you have periods, which go across. Periods are rows. You're going to see the periodic table lots this lesson. Now, noble gas is an element from group 18, and it has a full complement of valence electrons. So it has 8 outer electrons. And because it has 8 outer electrons, 8 is the magic number, so it's generally unreactive. Once atoms have 8 electrons in their outer shell, outermost energy level, they don't react. They only react to become more stable. Once they have 8 valence electrons, they are stable. And so it's extremely difficult to get them to react. Under extreme circumstances, scientists have tried to force reactions, and they were able to do that with xenon and fluorine, but it wasn't a stable compound. So it was just an extreme situation just to see if it were possible. Now, the period number of an element is the same as the number of its outermost energy level. So aluminum has its valence electron in the 3rd energy level, and it's in row 3. And because elements in the same group have the same number of valence electrons, that's why they have similar properties. So protons tell you the identity, the number of valence electrons, which is equal to the number of protons, gives us our properties. So for my example here, I said that, let me get my pen up. I said that aluminum is in row 3. So you have row 3 here, come over, and you see aluminum. Each period corresponds to the outermost energy levels. So we know that there are 7 energy levels. Hydrogen and helium are in the first, only have 1 energy level. Everything in row 2, or period 2, has 2 energy levels. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon all have 3 energy levels. Everything in row 4, period 4, have 4 energy levels, and so on. Now, group 1 is known as the alkali metals. Remember, groups are columns. They're families. They have similar properties due to their valence electron structure. Now, group 2 is known as the alkaline earth metals. Group 17 is known as the halogens. Halogens is the salt formers. So chlorine is in there mixed with sodium and makes sodium chloride, which is salt. Now, not all salts are table salts, but you have salts that will make with the group 17 elements. Now, group 18 is known as the noble gases. So noble gases are here. So here you have the noble gases. I'm going to abbreviate. Here you have the halogens. Here you have, with the exception of hydrogen, you have the alkali metals. And then here you have the alkaline earth metals. And you can see down here, we have a key that corresponds to the type noble gases here. So let's talk about physical states and classes of elements. There are only 2 elements that are liquids at room temperature. Those would be mercury and bromine. Mercury, they used to use in thermometers, and my mom who was also a chemistry teacher. She went to college in the 60s, and she remembers them telling her to play with it if the thermometer ever broke. They're like, it is so cool. And the teacher would keep liquid mercury that had broken in a little jar for his students to play with. Then they found out that it was highly toxic and bad for us, and they have changed using from using mercury in thermometers to using a type of alcohol. But it's still not good for you to ingest that. If it broke, they don't even make thermometers that have that in for your mouth anymore just because that's dangerous. Glass thermometers. But back in the 60s, that's what they did. And there are various types of alcohols that are not made to ingest. So gases, except hydrogen, are found in the top right corner. And synthetic elements are made through nuclear reactions, and they're marked mostly elements after 92. So if we look at the periodic table, you'll see elements that are marked as radioactive or synthetic. The majority of our elements are metals, like 90% of them. The metalloids are on the boundary of metals and nonmetals. So they have some properties of metals and some properties of nonmetals, and they are what are used as semiconductors. Semiconductors are what we use in our electronics, and they're the reason why they're able to have some heat with them, because their first computers, it had to be kept at a very strict temperature. You couldn't have too many people in the room because that would affect the temperature and it would melt down. It would just shut down. So when metalloids were discovered and successfully implemented, that made it more available to the public because it conducts heat and electricity, but not as well as our metals do. So here are metals in this area. You can see all of these are metals. All the left side over here up until these, which are this tannish color, are the metalloids. And then you have your nonmetals. As you can see, we have a lot of metals in the world around us. Metals are elements that have luster, they conduct heat and electricity, and they usually bend without breaking. They're malleable and ductile. They usually have extremely high melting points, with mercury being the exception. The transition elements are in groups 3 through 12 of the periodic table, and they are metals. This is where gold, silver, zinc, copper, nickel, those are all transition elements. The main group, metal chemistry, is predictable. Transition elements chemistry is less predictable. And that's because they have more complicated atomic structures and their orbitals have a lot more energy and can transfer the electrons more easily. So here in the middle, these are transition metals. Now there are two series of elements at the bottom of the periodic table right here. This is the lanthanide series, and this is the actinide series. And they're placed below the periodic table just to simplify the table. Otherwise, the periodic table would be twice as long. But removing it makes it more manageable and just placing it at the bottom. You just have to know that after 57 and 70, you have those column or those rows below the periodic table that you have to look at. Now, the first, like I said, is lanthanides. just because they follow the element lanthanum, and they're called the rare earth elements. And the second is called the actinides because they follow actinium, and they are all radioactive, and none beyond uranium occur naturally. Both of these series have unpredictable behavior, again, due to their complex structures. So here's lanthanide series, here's the actinide series, this is uranium, and you have plutonium, but all of these are radioactive. Now, nitrogen and oxygen make up 99% of Earth's atmosphere. There's a little bit of argon in there as well, but the main components are nitrogen and oxygen. Carbon is found in more compounds than all other elements combined. Nonmetals don't conduct electricity. They're poor conductors of heat, they're brittle when solid. Many are gases at room temperature and have lower melting points than metals. So here you have your nonmetals right here. You have carbon. They have a whole branch of chemistry devoted to carbon. It's called organic. We'll talk about that the last week. Nitrogen and oxygen. But all of these right here are all nonmetals. Metalloids, they have some chemical and physical characteristics of metals and other properties of nonmetals. They're along the border between metals and nonmetals, like I showed you before. Silicon, germanium, and arsenic are semiconductors, which are elements that don't conduct electricity as well as a metal, but does conduct slightly better than a nonmetal. So here are your your metalloids right here, this tan color. You have germanium and silicon and arsenic here. So let's do some practice. Go ahead and pause it and then come back whenever you've answered the questions and see and check your work. So here, a row across the periodic table is known as period. A column in the periodic table is known as a group. That should be a U, or a family. Remember, everything in a group or a family has similar characteristics. The majority of most elements are metals. And then this is practice naming the groups. So alkali metals, if you wanted to go back and look, what group are alkali metals? So if we look here, on the bottom, you can see alkali metals are red. Here are the alkali metals right here in group 1. So the alkali metals are group 1. Group 1. Noble gases, what group are they? So let's come back here. We look here, noble gas, group 18. You'll need to know this. So on your exam, you'll need to know what they are. For your quiz, you could use your notes, but on your exam, you will have to know it. And again, you could take your quiz as many times as you like. The highest score is going to be kept. The point of doing that is so that you can learn and understand as much as you need to, and to give you the practice that you need, and to know what you need to study. All right. We'll see you next time.